All right, let's just kind of begin with this. Whoa! Define linear momentum. Sorry, I just saw that right there. I'm going to write down my ideas like I do for all these questions, but I'll just be clear. We got a collision problem. I mean, I think you can kind of anticipate. I have given you so many collision problems. I mean, you just know there's going to be on the test, right? There is going to absolutely be a free response collision problem on the test. So I'm really glad I'm having you study this, and we'll do all this kind of stuff. So let me just tell you right now, we get this before and after the collision. I mean, right here, I'm going to want to write down MAUA plus MBUB. And then here I'm going to write an equal sign. Looks like they've got the same speed, so I'll say MAV plus MBV going at the same speed. You know, I just have this feeling, whenever I see this, I wonder, is B not moving just because I see a speed written here and not one here? So what I'm going to do is I'm going to go here and read, try to skim through, see, blah, 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 blah. Stationary truck B, there you go. Nice. So, man, do they give any kind of masses? Let me hunt around for that. Oh, so that's later on. All right, let's define linear momentum. I'll define it using an equation. So P equals mv. And what I'll actually say is it's the mass times the velocity. And I will note that it is a vector. Okay. Calculate the speed immediately after the collision. All right, let's do this. One thing I want to tell you, this formula that I'm going to give you, again, it's not on the data sheet. This whole momentum conservation, this principle, by the way, it has a name. It is called conservation of momentum. Which is awesome, and that's a great name, and it's absolutely not on the data sheet. This is one for the 3x5 card. Definitely put it on there, okay? Now let's go ahead and let's do a calculation. So we got MA, UA, plus MB, UB, equals MAV plus MBV. They're going at the same speed. All right, we're just going to throw in some numbers. 800 going at 5 plus, I'm going to keep this all at 0 because UB 0, I'm just going to multiply it 0. So I'm going to have 800 at V plus 1200 at V. So we get 4,000 equals 2,000 times V. So V ends up being 2 meters per second. Now let's get the total kinetic energy lost during the collision. This is a kind of a common thing. So here we go. So the kinetic energy before is going to be 1/2 times MA times UA squared, which is going to be 1/2 times 800 times 25. That's 400 times 25, which I think is going to give me 10,000 joules. And then after the collision, we're going to have 1/2. And let's add these masses. We've got 2,000, but now we're only going at 2 meters per second squared. So that's going to be 4,000 joules. So it looks like I'm losing 6,000 joules lost. What happens? There's a lot that can happen to this energy, but the most common thing, so lost to heat, noise, maybe friction of cars against each other. Okay. Heat and noise are the big ones, though. All right. There we go. And that is, you know what? I'm actually going to stop with this question here. I think we got a good idea of where this is going. All right.